Okay, so now I want to start section 5.3, the fundamental theorem of calculus. The fundamental theorem of calculus. There is two fundamental theorems of calculus, part 1 and part 2, and these two theorems establish the connection between the two branches of calculus. Differential calculus, remember how we derivative, so it's going to establish the connection between differential calculus, which is represented by the derivative, which we started using the tangent line problem, and integral calculus, which started from the area problem. So this is the section where we combine the two branches of calculus: differential calculus that started with tangent line problem, and integral calculus that started from the area problem. Okay, so let's start with the first fundamental theorem of calculus, the fundamental theorem of calculus, part 1. If f is a continuous function over a closed interval, if f is a continuous function over a closed interval ab, then the function g defined by g of x equals integral from a to x f of t dt. Notice the upper limit is a variable where x is between a and b, is continuous over ab, and differentiable over the open interval ab, and differentiable over the open interval ab. And if you find the derivative of g of x, so dg by dx, or g prime of x, so basically you're finding the derivative of the integral whose lower limit is a constant and whose upper limit is x, f of t dt. So you find the derivative of the integral, definite integral, from a constant to an upper limit x. It's going to be the value of the function at the upper limit. At the upper limit. And let me write down what it means. This means where the integrand, which is f of t, is continuous, the derivative of the definite integral, with respect to the upper limit, in this case the upper limit is x, equals the integrand evaluated at the upper limit. As long as the lower limit is constant. As long as the lower limit is a constant. As long as the lower limit is a constant. So the derivative of the definite interval from a constant to x, f of t dt, as long as the function is continuous over the closed interval ab and the differential over the open interval ab where x is between a and b, this equals the value of the integrand at the upper limit. That's the first fundamental theorem of calculus. Let's look at number 4, page 406. Number 4, page 406. It says that g of x equals integral from 0 to x f of t dt, where f is a function whose graph is shown in the book. So where f function's graph is shown, so you see the graph at the bottom of page 406, you all need to be looking at that. Part A. Use part 1 of the fundamental theorem of calculus to graph g prime. Okay, well, to find g prime, it's the derivative of the definite integral, which is f of x, and we already have the graph of x. Okay, it's already graphed for us. So this is the graph in the book. Part B. Find g of 3, g prime of 3, and g double prime of 3. G of 3, which is, if you look at the integral, it's the integral from 0 to 3 f of t dt. So if you look at the graph from 0 to 3, you have the area of a triangle plus the area of a trapezoid. Area of triangle plus area of trapezoid. The triangle is half base times height, half base times height. Half base is 2 and height is 1, 2, 3, 4, 5, 5. So base is 2. Now the trapezoid is half the height times the sum of the two bases. Half the height, so the height is 1 unit, half of it is 1/2, times the sum of the two bases. One base is 1, 2, 3, the other base is 5. 3 plus 5. So you get 5 plus 4 is 9 square units. That's g of 3. And then g prime of 3. Remember, g prime of x is f of x, so g prime of 3 is f of 3 equals f of 3, since g prime of x equals f of x, and f of 3 from the graph, it's 1, 2, 3. To find g double prime of 3, we need g double prime of x, which is going to be f prime of x. So g double prime at 3 is the derivative of f at 3, which you look at the graph, you can find the slope at 3, which is 5 minus 1 over 4 minus 2, which is 2. Part C. Does G have a local max, a local min, or neither at x equal 6? If you look at G prime is f of x, so at x equals 6, G prime is f, okay? So to have a local max or local minimum at 6, it has to change from decreasing to increasing or vice versa. So at 6, G prime is positive before 6, and G prime is negative after 6. If you look at it, so G prime is positive if x is less than 6, and G prime, remember G prime is f of x, we're looking at the graph, G prime is negative if x is greater than 6, so we have a local max at 6. X equals 6, and part D, does G have a local max, a local min, or neither at x equal 9? So look at x equal 9. g prime is negative if x is less than 9, and positive if x is greater than 9. So we have a local min at 9. At 9. Okay, number 10, page 406. Number 10, page 406. It says, use part 1 of the fundamental theorem of calculus to find the derivative of the function. So g of x equals integral from 1 to x ln of 1 plus t squared dt. Since the lower limit is constant, the upper limit is x, so g prime of x is going to be ln of 1 plus x squared. Okay, here's another example. Let r of y equals integral from y to 2 of t cubed sine t dt. Find r prime of y. Well, to be able to use the first fundamental theorem of calculus, the upper limit has to be in the this has to be switched around. So you know, from the rules of the integration, if we flip the limits, then it becomes the opposite. Okay, so we can flip the limits, then we get the opposite. So r prime of y is going to be negative, plug the y in, y cubed sine y. And here's another example. If y equals, so what if the upper limit is a function of x? It's not just x squared, x cubed, x to the 4, cosine squared theta d theta. So all you have to do in this case, using chain rule, since this is a constant, this is a function of x, you plug it in, but then you, according to chain rule, you get a times by the derivative of x to the 4 times by the derivative of the upper limit. So it's cosine squared x to the 4 times 4 cubed, which is 4x cubed cosine squared x to the 4. Be careful about this, okay? So the second fundamental theorem of calculus, the fundamental theorem of calculus, part 2. If f is continuous over a closed interval AB, then if you want to find the definite integral from a to b f of x dx, it's basically f of v minus f of a, where f prime x is little f of x. Basically, big F of x is an antiderivative of little f of x. So to evaluate a definite integral, all you have to do is find an antiderivative of the integrand and then plug the upper limit. So basically this is what we're doing. We're doing f of x between a and b. So you plug the b, you get f of b, you plug the a, you get f of a, and then you subtract. Where f of x is an antiderivative of little f of x. So all you have to do to evaluate a definite integral, find an antiderivative. We have all the antiderivative rules, and then plug in the upper limit, plug in the lower limit, and then subtract. Let's practice it. 26, page 407. So it makes integration, definite integration, a lot easier. From -1 to 1, x to the 100 dx. So we're going to find antiderivative of x to the 100, which is x to the 101 over 101. And then we put the limits in the same order, and then we plug the 1 in. 1 to any power is 1, minus, we plug the -1. -1 to an odd power is -1 over 101, so it's 2 over 101. 34 integral from -5 to 5 e dx. Well, e is the constant, so e integral 5 to 5 1 dx, which is e, and then integral of 1 dx is x, right? Derivative of x is 1, and then we plug the -5 and 5, upper then lower, so we plug the 5 minus -5, which is 10. Okay, now 38, the definite integral from -1 to 2 of 3u minus 2 u plus 1. So before we do antiderivative, we're going to avoid integral from -1 to 2, 3u squared plus u minus 2 du, which would, if you break it down, 3 integral -1 to 2u squared plus du plus integral of u du from -1 to 2 is 2 integral of 1 du from -1 to 2. So 3 u squared would be u cubed over 3 times 3 is u cubed, and then I'll do the limits one shot. I don't want to do it for every one of them. Plus integral of antiderivative of u is u squared over 2 minus 2 antiderivative of 1 is u, and then we plug in the limits, upper limit first, so it's 2 cubed plus 2 squared over 2 minus 2 times 2 is 4, and then minus, you plug the lower limit as -1 cubed plus -1 squared over 2 is 1/2 minus 2 times -1 is 2, and then if you do the math you get 9 over 2. Okay, let's do a lot of practice. Number 44, page 407. So the integral from 0 to 3, 2 sine x minus e to the x dx. So we can break down integral of 2 sine x dx minus integral from 0 to 3 of e to the x dx. We pull the 2 out. Antiderivative of sine is negative cosine, so negative cosine, and then minus integral of e to the x. Now we're going to do the limits. So -2 cosine 3 minus e cubed, and then minus f of b minus f of a, so -2 cosine 0 minus e to 0. So cosine 0 is 1, so that's -2 minus 1, which is -3, times negative is 3, so it's 3 minus 2 cosine 3 minus e cubed. Okay, so we did 44. Let's look at 54. Integral from -2 to f of x dx. Find where f of x equals 2 if x is between -2 and 0, and 4 minus x squared if x is between 0 and 2. Okay, so if we want to do -2 to 2, we have to do -2, so this equals -2 to 0, so we can find f of x plus 0 to 2 f of x dx. Go from -2 to 2 to 2, f of x is 2, so -2 to 0, 2 dx, plus from 0 to 2, f of x is 4 minus x squared. So this would be 2 outside, integral of 1 dx is x. This would, if you break it down, it's 4 dx minus x squared dx, which would be plus 4x, and then minus x cubed over 3. So this is 6x minus x cubed over 3. Don't forget, we're gonna do the limit. I'm sorry. Okay, let's fix this. So we got 2x. This one is between -2 and 0. We cannot combine them. Now this one would be 4x minus x cubed over 3, but this one is between 0 and 2. Okay, So this would be 2 times 0 is 0 minus 2 times -2 is -4, so it's +4. Plus this one, it would be 8 minus 8 over 3, and then minus zeros, and the answer would be 28 over 3. Let's look at 56, page 407. 56, page 407. It says, sketch the region enclosed by the given curve and calculate its area. So y equals x squared, y equals 0, and x equals 1. So y equals x squared, y equals 0, this is y equals 0, this is x equals 1, and y equals 0, so y equals x squared, 0, 0, 1, 1. So this is y, so in this, and that, so it's this area. And to find this area, it's the definite interval as we saw from 0 to 1 of x squared dx. Wait, is it x squared or x cubed? Oh, it's x cubed, sorry. So x cubed dx, so this would be x to the 4 over 4, which is if you plug the 1 in and then plug the 0 in, so it's 1 over 4. So that area is 1 over 4 square units. Okay, number 64. It says, what's wrong with this equation? What is wrong with this equation? Integral from -1 to 2 of 4 over x cubed. Well, if you look at 4 over x cubed, it's not even defined. It's not even defined, let alone continuous, not even defined over -1, 2. At 0, it's undefined. So we have, okay, that's what's wrong with this integral. Okay, let's look at number 70, page 47. We have f of x equals integral from square root of x to 2x tangent inverse t dt, and there's to find the derivative of this. But before we can find the derivative, we gotta split it up so we can use the first fundamental theorem of calculus. So we'll write integral from square root of x to 0 tangent inverse t dt, and then 0 to 2x tangent inverse t dt. Now the lower limit has to be a constant, so we make it a negative. Tangent inverse t dt, the lower limit is a constant, we're good. So now, using the fundamental theorem of calculus part 1, f prime of x equals negative, so you plug that in there, so you get tangent inverse root x, but then since this is not x, we times by derivative of root x, which is 1 over 2 root x. Same thing here, we plug the 2x in there, so it's tangent inverse 2x times the derivative of 2x, which is 2. So it would be negative tangent inverse of root x over 2 root x, plus I'll put the 2 up front, 2 tangent inverse of 2x. That's the derivative. So we had to break down the integral because we had a variable we had to bring a constant. You can 0 or any number in there, 1 or 2, doesn't matter. Okay. And that's all I wanted to do from this section. So until 5.4, have a good day.